Bismillahirrahmanirrahim. Dear students, this is our second lecture on engineering statics. We have earlier talked about three-dimensional force systems and we solved two problems on that. Uh, we will not be solving any more problems on three-dimensional force systems because in all the subsequent topics, that is in moment and couple in three dimensions, and then in resultants, and then in 3D equilibrium, we will be writing the force as a vector quantity in the problems that we are going to solve. So we will keep practicing this as we proceed with the following topics. So we will just be we will not be solving any more problems on three-dimensional force systems, but we will keep applying that. So we start today with the next topic, which is on moment and couple. This is our new topic, moment and couple. Now the basic calculation remains the same. In three dimensions, when we are calculating the moment produced by a force, it is very strongly recommended that you use vectors, because in 3D, when we calculate the moment produced by a force about any point, it is going to have three components. It will be having a component, moment will be having a component in x direction, about x-axis, about y-axis, and and z-axis. In 2D also, all the moments were about an axis which was perpendicular to the plane of the force and the position vector. However, all the position vectors and all the force vectors were in one plane when we were talking of 2D. So all the moments were always about perpendicular to that plane, which was the z-axis. So all the moments were about z-axis, and we were just talking about the counterclockwise moment positive, or clockwise or counterclockwise positive, whatever sense we select. But in this case, we will not be sure whether it will be very difficult to track the moment produced by the scalar components, because x component of the force will in general be producing moment about y-axis and about z-axis. Similarly, y component of the force will in general be producing moment about x-axis and z-axis, and z component of the force will in general be producing moments about x and y axes. And the directions of these axes also have to be seen. We cannot really it may not be really possible to just stick to one clockwise or counterclockwise convention. But in 3D figure, we will have to do a little bit of visualization. So it will be a very difficult task to use vectors. However, in a certain problem, it may be easier to. It is always easier to use scalars, and wherever it is possible, you should be looking for an opportunity to use scalars. However, it may not be possible in many problems. So in general, we will be using vector method in three-dimensional moments. The basic formula remains the same, which we have already studied in 2 dimensions. That is, m is equal to r bar cross f. Since we are using the vectors, so we will be just talking about this cross product formula. M is equal to r bar cross f. The only difference is going to be that now r bar is going to have three components in general, and force is going to have three components in general. So r bar is going to be rxi plus ryj plus rzk, and similarly f is going to be equal to fxi plus fyj plus fzk. And then we will have to just take the cross product, r bar cross f, which will give us moment about a point. Taking the cross product, this we have already discussed that r bar cross f must be maintained. M is equal to r bar cross f. It is not equal to f cross r bar. F cross r bar will give us the opposite direction of the moment. So r bar cross f is going to give us the correct direction of the moment. Now evaluating the cross product should not be a problem. You can just write the two vectors and then take the cross product of the unit vectors I, j and k. I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. Similarly, when we reverse the order of the cross product, it becomes negative. So j cross I will be equal to minus k. So we can use that, write the two vectors in terms of I, j, k, and then take the cross products of the unit vectors. And we can also write it in a determinant form like this: I, j, k, then the components of r bar, the components of the first vector which is r bar, then components of the second vector which is f, and then we can evaluate this determinant. So it gives us the result which is shown here. MO is equal to R phi Fz minus Rz Fy I, and so on. So this was simple moment about a point. We just have to write the position vector and the force vector. The only difference from two dimensions is going to be that now the position vector and the force vector are going to be in three dimensions. They are going to have an additional component. Next we talk about movement about an arbitrary axis, movement about a line. So if you look at this figure 2 by 2, 3, we have a force vector and we have a line lambda. So this line lambda, along this line we have to find the moment produced by the force along this line. The procedure for this is that we first take moment about any convenient point on that line, any point which is known to us. So we take any point O, which is a known point on this line, and then we take moment produced by the force about this point. Moment produced by the force about this point is going to be, of course, when we are calculating the moment, we have to write the position vector. Position vector will always start from the point about which we are taking the moment, and it will go up to any point on the line of action of the force. So this r bar is the position vector up to any starting from point O up to any point on the line of action of the force. So we can write this position vector r bar, and we can also write the force vector F, and then we can take r bar cross F, that is going to give us moment produced by the force about point O. Now this moment produced is going to be, since it is equal to r bar cross F, and this cross product will result in a vector which is going to be perpendicular to the plane of the two vectors r bar and F. So this is going to be perpendicular to r bar. It is going to be perpendicular to F. Now what we do is, next we take the projection of this moment about point O onto line lambda. And how do we take the projection of a vector onto a line? We draw a perpendicular from the head of the vector onto that line, and wherever it intersects that line, that is going to give us the projection of that vector onto that line. Or in simple words, as we have studied at the beginning of the course when we talked about the projection and components, this is going to be just equal to vector MO and taking its dot product with the unit vector along the line. that will give us the projection along line lambda. So we have to find unit vector along lambda and then take dot product of MO with unit vector along line lambda, and that is going to give us the projection of MO on line lambda, and that is going to be the moment about this line lambda, because MO, this vector MO which is shown in the figure, this is the moment about this is the direction of the moment. This is the direction of the moment which is perpendicular to the plane of r bar and f, and then this direction is actually determined by the right hand rule, rotating from the first vector which is r bar to the second vector f. So this gives us the direction of MO, and when we take the projection of this onto line lambda, so it is going to give us moment about line lambda. So r bar cross f dot n, it is going to give us the magnitude of the moment. And then if we are to find the moment as a vector quantity, then any vector quantity can be written as its magnitude multiplied by the unit vector along this line. So if we are to write m lambda as a vector quantity, we know the magnitude is equal to r bar cross f dot n. Magnitude is equal to r bar cross f dot n. Moment produced about point O dot n. R bar cross f is moment produced about point O, and dot n will give us the projection of this moment onto line lambda. So that is m lambda, which is the moment about magnitude of moment about line lambda, and when we further multiply this magnitude of m lambda along the unit vector in the direction of this line, which is again the same n, we just multiply the magnitude with the same unit vector n, and that is going to give us the moment vector. So when we are to take moment produced by a force about a line, we first have to take moment produced by the force about any point on that line, and then we have to take dot product of this moment about a point on that line with the unit vector along that line. That is going to give us the magnitude, and if we are to find the vector, if we are to find the moment about that line as a vector quantity, then we have to multiply this magnitude with the unit vector along that line. So that gives us moment produced by a force about a line. In 2 dimensions, we talked about Vérigton's theorem. Moment produced by a force about a point in 2D was equal to sum of the moments produced by its components, vector sum of the moments produced by its components about that point. So that was Vérigton's theorem in 2 dimensions. In 3 dimensions, it states that if we have a number of forces, say F1, F2, F3 and so on, we can have as many forces as are given. So but this is applicable to a system of concurrent forces only. So say we have 3 concurrent forces who have a common point of their lines of action, have a common point of intersection. So all the concurrent forces, in case of all the concurrent forces, the sum of the moments about point O is going to be equal to the moment produced by the sum of these forces. Sum of the moments produced by each force separately will be equal to moment produced by sum of these forces, or you can say moment produced by the resultant. So whatever is the moment produced, whatever is the total moment produced by all these three forces, moment produced by F1, then moment produced by F2 and F3, say M1, M2, M3 are the moments produced, then M1 plus M2 plus M3 will be equal to moment produced by their resultant, that is R bar cross summation F. So that is Varignon's theorem in 3 dimensions. It is applicable to concurrent forces only. So in case of concurrent forces, moment produced, sum of the moment produced by all the forces about any point O is equal to moment produced by the resultant of the force about that point. So that will reduce your effort of taking cross products. You can just sum the forces and then take one cross product with the vector r. In this case, vector r will have to be taken from the point O about which we are finding the moment up to the point of concurrency. R bar is going to be, you will not have a choice on R bar in this case. R bar will be from point O to the point of concurrency, which is point A in the figure shown. Couple in 3 dimensions, again it is going to be, couple is a free vector. It is going to have same value at all the points. However, the direction of this couple is going to be perpendicular to the plane of the 2 lines, plane of the 2 forces. So it is going to be perpendicular to the plane of the 2 forces. And if you are to calculate the value of the couple, then we can select any point on the line of action of one force and we can select any point on the line of action of the other force, and then we can write position vector R bar. In this case, point A is on the force plus F, point B is on the force minus F, and he has taken R bar directed from point B to point A. Remember, position vector R bar is always directed towards the force. Position vector R bar is always directed towards the force. So if you are taking R bar from B to A, then the force that you will take is going to be plus F. However, if you take the position vector directed from A to B, in that case the position vector is directed towards minus F. So the force that you will take for calculating the moment is going to be minus F. So that is how you can calculate the moment of a couple in 3 dimensions. You just take any point on the line of action of one force and any point on the line of action of the other force, and then write R bar, take the cross product with the force towards which R bar is directed. Next, we just solve one problem on 3-dimensional moments in couple. This is problem 2 by 121, in which we have 2 forces of equal magnitude which are parallel to each other, so they form a couple. 150 Newton force we have two forces acting on the handles of the pipe wrenches, and these constitute a couple M. We have to express the couple as a vector. So we can consider any force. Say we select in this say we select 150 Newton force, which is directed downwards as the force. So this is going to be minus 150 K. The force vector is going to be minus 150 K. Now we have to write R bar. For R bar, we have to select a point on the line of action of one force, any convenient point on the line of action of the one force, and we have to select any point on the line of action, any convenient point, any known point on the line of action of the other force, and then join these two in the direction of the force that we are selecting for calculating the moment. So if we select 150 Newton force, which is directed downward, as the force for calculating the moment of the couple, then the position vector is going to be directed from the point on the wrench with 150 Newton force in the upward direction to a point on the wrench where we have the 150 Newton force applied in the downward direction. So the direction of the position vector is going to be this. So we can write the coordinates of these 2 points. So if you look at the axis system, the origin is at the center of the pipe on the wrench on which we have 150 Newton force in the downward direction, wherever this wrench is holding the pipe. In that case, at that point, we have the origin of the axis system. So if you consider the 150 Newton force which is directed upward, then the point where this force is applied on the wrench, that point is 150 millimeter behind the origin in the x direction. So x coordinate is going to be minus 150. And similarly, from that place, when we move in the y direction, we have to go in the negative y direction. So the coordinates of point on the 150 Newton force which is applied in the upward direction, the coordinates of this point are going to be minus 150 and minus 250. Of course, the z coordinate is 0 because this point is in xy plane. So minus 150, minus 250 and 0. The point on the 150 Newton force directed downward, this point is on the y-axis. So x and z coordinates are going to be 0 and the y coordinate is along positive y, which is 250. So the coordinates of this point are going to be 0, 250, 0. So when we subtract the coordinates of this point, when we subtract the coordinates of the point on the 150 Newton upward 150 Newton force from the coordinates of the point on the 150 Newton downward force, so it is going to be 0, 250, 0, minus 150, minus 250 and 0. So the difference of coordinates will give us plus 150i and plus 500j. Z coordinate is 0 for both the points, so Z coordinate will be 0. So the position vector directed from the upward force towards the downward force is going to be 150i plus 500j. So you can take cross product of this position vector with the downward force, and downward force is minus 150k. Positive z-axis is going to be upward according to the x and y directions which are shown to us. Positive direction is going to be in accordance with the right hand rule. If we curl the fingers of our right hand, in the direction of rotation from x to y, it is going to indicate the positive z direction, which is going to be upward. So this 150 Newton force, when we write this in vector form, this is going to be minus 150 K. So the moment of this couple is going to be equal to R bar cross F. R bar is equal to 150 I plus 500 J, or you can convert this to, as the answer is given in Newton meters, we can convert this position vector to meters. So it is going to be 0.15 I plus 0.5 J. 0.15 I plus 0.5 J meters cross minus 150 K Newton, which is the force, and when we take the cross product, we will get the result, which is shown here, minus 150 into 0.5, and this is going to be I, and 150 into 0.15 J. So this is the result, minus 75 I plus 22.5 J Newton meter. So you should know how to write the position vector. We have to select one point on the line of action of one force and one point on the line of action of the other force, and join these 2 points in the direction of the force for which we are selecting for calculating the moment. So that will give us R bar, and then we write the force as a vector quantity and take the cross product, which will give us the moment. Thank you.